In this lesson, we'll discuss curvilinear motion using normal and tangential components. Normal and tangential components are often used to study the circular motion of bodies, such as the persons on this amusement ride. Now, before we discuss these components, let's first see how they're established. Any curved path is made up of a series of small differential arc segments. Each segment, like this one ds, has its own center of curvature O' and a radius ρ to make the arc. Here, for example, is another one, and here is a third one. By considering these small arc segments, of course, we create the entire path. Now, the normal and tangential coordinates are established based on this idea. They're actually fixed to the path. The tangent axis acts tangent to the path where the particle happens to be located and is positive in the direction of motion. The normal axis acts toward the center of curvature of the path at the point, so it goes this way. How about down here? Which way do the t-axes act here? Well, the t-axis this way, of course, and the normal axis up like this. And finally, when the particle is located here, and again the axes are fixed to the path, which way does the tangent axis go? Like this, and the normal axis goes this way. Now, as a real-life example, consider this Ferris wheel, which is rotating around this way. If we consider the gondola up here, which way would the tangent axis act? This way, of course, tangent to the circular path, in the direction of motion. And the normal axis? Why, it acts down, toward the center of the circle, doesn't it? And again, remember, these are fixed in space, and this gondola just happens to come up and meet this point. Now, in 3 dimensions, a third axis is needed, and we refer to that as the binormal axis. It's perpendicular to the plane of motion. And remember, within the plane of motion, we always have the n and the t coordinate axes. There's no motion in this direction. Now, with this in mind, let's see if you can establish the n, t, and b axes for this motorcyclist as he rounds this curve. Which way does the tangent axis act? Why, it's tangent to a circular path, isn't it? So it goes this way, horizontally, of course, in the direction of motion. The normal axis? It has to act in toward the center of curvature. And finally, the binormal axis. Well, that acts perpendicular to the road, doesn't it? In other words, the plane of motion is in the nt plane, and the b-axis is perpendicular to it. Now let's discuss some kinematics related to the nt coordinate system. First, we'll consider a fixed point on the path, right here, and we'll locate the position of the particle relative to this point using a position coordinate s. This position coordinate, of course, is positive in the direction of motion. The nt axes are set up on the path also as a fixed point, and the particle just happens to be up at this point, this instant. If I'm able to find the time rate of change of the position coordinate, then I'll be able to define the velocity of the particle. That velocity vector will always be tangent to the path, and we can find it using this key equation. V is equal to ds dt. Same equation we used before for rectilinear kinematics. Now, of course, the change made in the velocity vector with respect to time will give us our acceleration. For example, when the particle's here, it has a velocity v, and when it moves to this position, it has a different velocity, v plus delta v. Here's an addition of the components, v plus delta v, giving us our resultant velocity. I can take this change in velocity and I can break it into 2 components, in the tangent direction and then in the normal direction. Notice that the tangential component is telling us how the magnitude of the velocity v is changing. So in other words, this length would be equivalent to this length. The change in the normal direction will tell us how the vector is changing its direction, how much it swings up into this position. Let's look at each of these components separately. In the tangential direction, if I take this component, divide by delta t, and then take the limit as delta t approaches 0, I'll get the tangential component of acceleration. Here it is. A sub t is equal to dv over dt, and it represents the change made in the magnitude of the velocity. Now realize that since v is equal to ds divided by dt, or actually dt is equal to v divided by ds, then I can substitute that in for dt here, and I can cross multiply and write this equation in this form. In other words, I've eliminated dt here, and I have an equation which relates the variables a sub t, s, and v. And of course, these two equations are similar to what we had for rectilinear motion. Now let's discuss the change made in the normal direction for the velocity vector, delta v sub n. Notice that it gives us the change made in the direction of v. The angle between the two vectors, here and here, is delta theta. And I can write a relationship between this change and the velocity v and delta theta. It looks like this. Actually, this equation is similar to the equation in geometry. S is equal to theta times r, where theta, of course, is in radians. But here, I'm saying that r is equal to v. It is true that we also have this little delta vt term added to it, but this is a differential size. So essentially, we can consider v with this changed angle, delta theta, to get us from here up to there, and this arc length then is delta v sub n. Now, apart from this, we can also look at the situation like this. Here's our particle with a velocity v, and here it is with the velocity v plus delta v. And the arc length right in here is delta s. And here, of course, is our delta theta. That angle, of course, is the same as the angle right in here. Again, using the same idea of geometry, s is equal to theta r, I can write this equation. Delta s is equal to rho, the radius of curvature of our path, times delta theta. Now, I can solve for delta theta in this equation and substitute it right up in here. And when I do that, I get this equation. In other words, delta theta is equal to delta s over rho, which is indicated here. Finally, I can take the time derivative of each side of the equation. When I do that, on this side I have delta v sub n divided by delta t, and over here we have delta s divided by delta t. We know this to be the velocity in the limit, and this, of course, becomes a sub n, the acceleration component in the normal direction. Therefore, this v will multiply by this one and give us this equation. V squared divided by rho is equal to a sub n. The normal component of acceleration, then, as indicated here, is giving us our change made in the direction of the velocity, just like the tangential component of acceleration is giving us our change made in the magnitude of the velocity. And it's for this reason that we separate the change in the magnitude and the change in the direction that we've chosen to use nt coordinates. Finally, in some problems, we're given the path along which the particle travels in terms of x and y coordinates, like this path, y equals a function of x. And we need to know the radius of curvature if we're ever to find, say, the normal component of acceleration. You can do that using this formula from calculus. The radius of curvature is simply found by taking the two derivatives of our path function, substituting them into this equation, and evaluating at the point x where the particle happens to be located. It's a formula you may want to keep in mind when we go to solve problems. Let me demonstrate a few of these ideas with a problem. Here we have a box which is moving down this ramp at a constant speed of 20 meters per second. And we're asked to determine the radius of curvature of the path and the tangential and normal components of acceleration when the distance x is equal to 12 meters on the path. To solve the problem, though, first we'll have to determine the radius of curvature rho at this point. course, that requires using this equation. Now, in order to obtain the two derivatives we need, we go to our path function and we determine, first, dy over dx. What's that equal to? Well, it's simply 1 over 12 times x. We have to evaluate this at x equaling 12, and so if we do that, we get an answer of 1. Now let's get the second derivative. D squared y dx squared. What's that equal to? Well, it's simply 1 over 12, isn't it? Now that we have these two numbers, we can apply our equation and get our value for rho. So we'll do that next. Rho is equal to, and here we have on top 1 plus 1 squared, all of this raised to the 3/2 power, of course, and then we divide it by 1/12, and if you work all this out, you get the result. It's 33.94 meters. In other words, the radius of curvature of the small ds curve that's made right here. It's going up here to a center of curvature. Now that I know it, I can find my two components of acceleration. In the tangent direction, we know there's no increase in the speed of the particle. The magnitude change of the velocity vector is 0. And so this term is simply d20 dt, or 0. Now we'll get the normal component. There, of course, we take our value of the velocity, which is 20, of course. We're going to square it, and we're going to divide it by our calculated value for rho, which was 33.94. And when you work this out, you get this value, 11.8 meters per second squared, our change in the direction of the velocity vector. And again, there's no change in the magnitude of that vector. So our acceleration is actually directed up in the normal direction in this particular problem. So having finished the problem, now we'll end our lesson.